In the previous videos, we looked at probability distributions that were discrete for discrete random variables. In this video, we're going to introduce the idea of a continuous random variable and probability distributions representing these continuous random variables. And in particular, one that we're going to be interested in is what's called the standard normal distribution. So we'll come to that in a minute. So in short, we're moving from discrete. So for example, the binomial distribution was a discrete probability distribution, as were sort of the generic ones we used when we looked at the game of roulette and number of siblings, things like that, for example. So we're moving from these discrete probability distributions and we're moving to continuous ones. So a good way to think about this is if we look back at some of the probability distributions that we already looked at, and we look at their probability distribution histogram, which is basically, I said at the time, we would more or less use interchangeably. So we have our x on one axis, p of x on the other, and we have a few different basically bars in our histogram that give us some shape like this. So this is an example of a case that is discrete. And as you can see, there's only a handful of possible values of the random variable x. In this case, I've got 1, 2, 3, 4, 5, 6 bars. So we've only got 6 values of the random variable x. So there's only few values of x. Well, if we start to increase the number of values of x that we're interested in, what would happen is our shape of our curve might look something more like this. So we'd move to something, again, I've got x on my horizontal axis, p of x on my vertical axis, but now we'd have a lot of bars. And so maybe it would look something like this. So allow me to just finish drawing all of these. So again, this is still discrete, but we have many possible values of our random variable x. And if we continue this onward and use even more values of x, so again, the idea of discrete is there's gaps between the possible values. So maybe over here we've got 1, 2, 3, 4, 5, and 6 are the numbers. And maybe over here we start keeping track of decimals. So it's, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, all the way up to 6. And so we have a lot more bars. What ultimately happens if we continue this procedure is eventually we'll get to the point where instead of dealing with individual values of x down here, we'll just treat it as a continuous variable, meaning we won't look at the individual gaps between the values, and instead of drawing individual bars, we'll just look at basically a smooth curve and just say this is the shape of this probability distribution. So we've gone sort of from this really blocky case to a case with a lot more bars that's starting to kind of look like just a smooth curve, and then eventually we'll just say, okay, let's just treat it as a smooth curve. One thing I want to point out, you'll notice I didn't write p of x up here, and that's because it isn't quite p of x. We'll talk about what this value is on this vertical axis as we switch to a smooth curve like this, but it's not the same as we had in a discrete case. And instead, it winds up being called, so these ones over here are what we call probability distribution functions. This one's going to be what we call a probability density function. So when we're dealing with a continuous case, the initials stay the same. It's still going to be a PDF, like we saw on the calculator, for example, binom PDF, binom CDF. We still have those same letters in the case of a continuous one, but now it's going to stand for a density function instead of a distribution function. So we call the continuous version of this curve a probability density function. And again, this new wording has to do with the fact that the axis no longer just represents probability. It's going to represent something a little bit different, and we'll take a look at that in a minute. So this is our probability density function or probability density curve. So let's look at an example and see how this might work. I want to think about the age at which people get their first driver's license. So when do people get their first driver's license? So we want to know the age at which people get their first driver's license. And I'm going to look at a curve representing this. So in this case, I'm going to draw a picture of this. X, my random variable, is going to be this age. So we're going to let X be the age at time of license. So at the time that they get that first license, how old were they? And if all we cared about is how many years old they were, this would be discrete. So if we said, were you 15 or 16 or 17 or 18, if that's all we cared about, X would be a discrete random variable. But the reality is that's not how we age. We age continuously. I want the exact age at the time they got their driver's license, down to the nanosecond, essentially. And so with that in mind, if my recollection is correct, I think in New Mexico at least, you have to be at least 15 to get your driver's license. And even then, I think it's typically a provisional license for a certain amount of time. But let me just mark out a few of these values. So 15, maybe up to 16, 17, 18, 19, 20, and so on and so forth. And maybe the curve looks something like this. It'll continue on that way. Again, I'm not going to call this P of X over here. It's going to be some values, and we'll talk about what those values are in a minute, but maybe this is going to be, let me break this one up as well. I'll say this is 0.1, 0.2, 0.3, 0.4 up here. Okay, so here's kind of what our picture is looking like right now. And you can see, again, we're representing this as a smooth curve. So on the bottom down here, we have the age at the time of the first license. And over here, we have something that's related to probability, but it isn't exactly probability. So we'll look at that in a minute. Let me just leave this blank, and then we'll talk about it in a minute. Okay. The way that we deal with one of these continuous curves is we want to think about the area under the curve, and that's going to be the most important thing. In this case, the area under the curve represents the probability. And so if I were to look at just, say, this section right here, the area of this section, so this area represents the probability that somebody got their driver's license basically between their 17th and 18th birthdays. between 17th and 18th birthday. So normally these are people we would refer to as 17-year-olds. This area corresponds to all the 17-year-olds, but you can see we differentiate between somebody that just turned 17 and somebody that's about to turn 18. So this region right here going horizontally represents an entire year's worth of time in our random variable x, which again is age, so it's measured in years. So right here is 17 exactly, the nanosecond you turn 17. Maybe here's 17 in a couple of months, here's 17 and a half, 6 months in. And you could pick any specific time. You're interested in, 17 years, 3 months, 13 days, 4 hours, 15 minutes, and 27 seconds or something like that. You could find that exact time somewhere on this axis. That's what we mean when we say continuous. I want the exact value. So the area is what represents probability, not the height. When we were dealing with these discrete cases, the height of the bar corresponded to probability, but now it's area under the curve. And so if you wanted to kind of approximate this and think about how we could figure out the area of this region, normally and this is actually what's done in calculus when we talk about areas, we can approximate it. Let's do this a little better. Approximate it with a rectangle. And that one's even not very good. Let's do a little higher here. Okay, good enough. The idea is that this rectangle is pretty close to the same amount of area. The little white region here that's left out of the rectangle almost matches this region over here. You could think about flipping that down into here. And the area of this rectangle would match. How do you find the area of a rectangle? Well, you do the width times the height. And the width of this rectangle is 1 year. So if I want the area, which is equal to width times height, and I want that area to represent probability. So let's just abbreviate that probability. And we already said is the width is 1 year. What does the height have to have units of? It has to have units of probability over years. It has weird units. So this is called dimensional analysis, just thinking about what the units are going to give us. The idea is that when you multiply two numbers together that have units associated with them, you also have to multiply the units. So if I want something, the end result of this to have units of probability, and I'm multiplying something that has units of years times something else, and I want it to end up spitting out probability, that something else that I'm multiplying it by must have probability divided by years. So that way when I multiply these together, the years would cancel, and we'd just be left with units of probability. And so this is the height, what it represents. It doesn't represent probability by itself. It represents probability divided by, in this case, whatever the units are of x. In this case, it was years, but that's why we call this thing a probability density function. We're taking the probability and dividing out by this other unit, x. And that's kind of the idea behind density in general. It's some quantity divided by another quantity. Normally, when we think of density, it kind of tells us how much stuff there is in a given amount of volume, right? So like the density of a pillow full of feathers is a lot different than the density of a bag full of concrete or something like that. And that's because in that case, we're looking at sort of the total mass divided by volume, but the division is what's important. And so in this case, it's probability divided by whatever this random variable happens to represent, which in this case, again, is years. So these are the units along the vertical axis. It's probability divided by whatever the random variable happens to represent. And that's why we call it a probability density function. Okay, so this is the most important idea. Area under the curve is equal to probability. This is the most important takeaway from this entire section. We're going to be using this concept for the rest of the semester. area under one of these probability density function curves, one of these, the area under it, corresponds to probability. So right here, this is the probability of somebody getting their driver's license between their 17th and 18th birthday. It's represented by whatever this area happens to be, which it looks like about 0.2 according to us, right? The height of that looks like about 0.2. It was 1 year wide. So we'd have a 1 year here. This number over here was 0.2-ish. That is a horribly drawn 0.2. Times 0.2 gives us 0.2 as the probability. So 0.2, 20% chance it looks like that somebody got their driver's license between their 17th and 18th birthday. One other question that I can ask then is, what is the probability that somebody got their driver's license at exactly the nanosecond they turned 17? So what is the probability that someone got their license at exactly the age of 17? And this exact is important. I don't mean sometime during their 17th year. I don't mean something when they were 17 years old. I don't mean on their birthday even. I don't mean on the day they turned 17. I mean they were given their driver's license the exact less than a nanosecond that they turned 17 years old. What is the probability of that? Well, hopefully it's obvious that that probability should be pretty slim, right? It's not very likely. Sure, there's lots of people that got their driver's license sometime during the year that they were 17 years old. There's going to be a lot fewer that got it on their 17th birthday on that sometime during that day. And there's going to be essentially nobody that got it the exact nanosecond that they turned 17. And this actually agrees with what we see over here. Area under curve equals probability. So if I'm interested in the idea that they got their license exactly when they were 17, what is the width? So in here, in this one, we had an entire year's width for the year they were 17 years old. But now I want it to go down not to 17 that whole year, but not even just the day they turned 17, which would be a much tinier little piece of this, but the exact nanosecond. Well, what is the width gone down to? So again, probability is going to be equal to the area under the curve, which in this case is going to be the height times the width, essentially, of this little rectangle. But the width, I'm saying, is going to 0. We have a 0 span of time, right? This represents time. The width represents time. How much time has passed over the instant that they turned 17? Well, 0 time has passed. That's why we're calling it an exact instant. So 0 time has passed. Has passed during the instant, the exact instant they turn 17. So the width is 0. If the width is 0, it doesn't matter what the height is. What is the overall probability going to be? The probability is going to be equal to 0. Any number you want to plug in here, if you're multiplying it by 0, you're going to get 0 out of it. The area under the curve is going to be 0. And this is a really counterintuitive idea for a lot of people. But it kind of makes a little bit of sense when you think about it as shrinking down from talking about the entire year that they're 17, down to the day they turn 17, down to the minute they turn 17, down to the absolute nanosecond they turn 17. When you shrink it down to a single instant, the probability that x is exactly equal to some value is 0. It only makes sense when we talk about one of these probability density functions to talk about an interval of time, not an instant. A single instant doesn't make sense. Sure, it makes sense to talk about between their 17th and 18th birthday, that interval of time, but it doesn't make sense to talk about x being exactly equal to some exact instant in time. So this is kind of weird. This is one of the weird paradoxes, essentially, of calculus. So I don't want to get into it too much, but the idea is how many instants in time are there? Well, there's an infinite number of instants in time. How long does each one last? It lasts 0 amount of time. And so we're finding a weird way to combine an infinite number of single instants in time, each of which individually has a probability 0 of being the time that this person got their driver's license, but which somehow add up to some finite value, in this case, 0.2. So it's very, very weird. We're adding an infinite number of zeros, essentially. And because of the weird way that infinity is defined and the weird way that 0 is defined, they combine in just such a way that we get this weird finite result out of it. So this should be kind of weird and counterintuitive. If you want to learn more about it, take calculus, and it'll make more sense if you actually do that. But this is kind of the idea. So it only makes sense to talk about the probability that x falls into some interval. So single instants don't make sense. Let's write these as bullet points so you see them in your notes. The probability that x is equal to a value is always going to be 0. It only makes sense to talk about the probability that x falls between some values. So for example, we could say a less than or equal to x less than or equal to b. That makes sense. So x equals a doesn't make sense, but x falling between a and b, that does make sense. Okay, so hopefully this, despite being a little bit counterintuitive, is starting to come together. One other question I want to ask is, what is the total area? Area under the curve. So let's get this all on the screen at once so we can ask this question. What is the total area underneath this curve? The total area has to be 1. The total area under any probability density function curve will always add up to 1. Why? Why does that make sense? Essentially, the question we're asking here is, we're interested in the age at which somebody got their first driver's license. And you can see our curve here starts at the age of 15. And it goes on, and this arrow over here is meant to indicate that it goes further this way. We didn't bother drawing it because there's not very much area under the curve over here. But it's absolutely possible that somebody could get their first driver's license when they turned 40 or 50 or 60 or 100 years old. Right? It's less likely. That's why there's not very much area under the curve way out here for these higher ages. Most people get it when they're fairly young, but it does happen. It's possible. So the question we're asking then is, to figure out the total area, what we're asking is, what is the probability? So somebody has a driver's license. What's the probability that they got it sometime between the time that they turn 15 and all the way out where this ends, which maybe we could say is, 200 years old, right? Nobody's ever lived that long. So certainly everybody that's ever gotten their driver's license got it sometime between when they turned 15 and when they turned 200 years old. And that means that the total probability should be 100%. There's a 100% chance that if you find somebody that that has a driver's license, that they got it between the time they turned 15 and 200. And that 100% chance needs to then correspond to the area under the curve. 100% corresponds as a probability, as a proportion to the number 1. So in this case, the idea is there is 100% chance that somebody with a driver's license if I can write driver's license, there's a 100% chance that they got it between the ages of 15 and whatever the upper bound you want to use. 150 years old is probably fine, but we'll just say 200 years. Call it infinity years. Doesn't really matter. We didn't specify how far to the right that graph goes, but at some point it becomes kind of irrelevant. We don't really care because there's so little being contributed to the area of that curve. So the probability has to be 1. So this is another important point. So I'll write it as a bullet point. The total area under the curve, zoom back in here, under the curve, right neatly, is 1. So these are the important points. The probability that x is exactly equal to some given value is always 0. Doesn't make sense to talk about x being exactly equal to a value. It really only makes sense to talk about x falling in some interval, some range of values from a to b maybe. So maybe from, as we just talked about a minute ago, from 17 to 18 over that interval. The total area under the curve always has to be 1 because it always represents 100% of all possible outcomes. So that total area has to add up to 1. Okay, so everything we've talked about so far, all of these ideas that hopefully make some sense, these all refer to just generic continuous probability density functions. We haven't talked about the standard normal distribution yet. So let's move on to that. So the standard normal distribution. Turns out the standard normal distribution is one type of continuous probability density functions. So let's think about what types of properties this thing is going to have. So the standard normal distribution, and we'll get to that in a minute. Let me just start with the normal distribution, and then we'll talk about what the word standard means. The normal distribution is another special case. Similar to how we talked about the binomial distribution, it happened to be a special case that just shows up a lot in practice. The normal distribution is a special case that happens to show up a lot in practice in real life. Okay. There are a few characteristics of a normal distribution. So what are the characteristics? Or you could think of it as kind of similar to the five requirements we had to determine if something satisfied being a binomial distribution. Same thing here. What are the characteristics that make something satisfy being a normal distribution? The first characteristic is that it only has one peak. So if you look at the graph, there's only one peak, or mode. If you remember that the mode is going to be sort of the highest point on our graph. So we have a curve that only has one peak. So the curve that we just looked at only has one peak, right? Here is the peak of this graph. So far, that one's still potentially in the running for being a normal distribution. Characteristic number 2, it is symmetric around that mode, or that peak. So that rules out this one from being a normal distribution because it is not symmetric. You can see it has a long tail on the right, having to do with the fact that there's no upper limit to what age you can be to get your driver's license, but it has no tail on the left, indicating that there is a lower boundary, right? You can't get a driver's license when you're 5 years old, at least not here in New Mexico. Okay. Oops. Criteria number 3, or characteristic number 3. The mean, median, and mode are all the same. They all have the same value. And essentially, this kind of just reinforces the same point that we just talked about. It means that this distribution is symmetric. We talked about being skewed left or being skewed right and how that affects the mean and the median, how they fall relative to one another. Well, when something's symmetric, the mean and median fall right on top of each other. And because this also only has one peak, it must also be right where the mode is. So the mean, median, and mode are all the same value. This reinforces these 2 points that we just saw up here. The last point is probably the most important one, and it's that it follows something called the empirical rule. It needs to follow the empirical rule. And if you read the textbook back in chapter 3, you may have run across the empirical rule, but I didn't cover it in the videos back then because I knew we were going to spend a bunch of time talking about it now. So what is the empirical rule? The empirical rule tells me basically how much stuff falls, or how much area falls within certain regions of this curve. So let me draw the picture. A normal distribution that we're talking about here is commonly referred to as a bell curve. You may have heard that term before. So if I draw a bell-shaped curve, so here's going to be my horizontal line. Again, that represents all the possible values of x, whatever the random variable is. And I make it bell-shaped. So here is my bell-shaped curve. This is something that if you see something like this, it's a good chance that it's going to be a normal distribution. But there are a few other criteria. So far, this picture only has one peak, and it's symmetric around that peak so that the mean, median, and mode are all the same value right where I just drew this vertical line. So this satisfies the first 3 criteria. In a minute, I'm going to draw some extra things to indicate that it also will follow the empirical rule. So what is this point right here at the center? Well, we said it's the mean, median, and mode. The easiest one to keep track of is the mean. So I'm going to label the center of our graph here. Let's draw that a little bit bigger. I'm going to label it mu because that's what we use for the mean. This is the mean of our distribution. I'm going to move now 1 standard deviation in either direction from here. And when I do that, I get a picture that looks like this. So I'm going to chop this up and divvy it up into sections. Roughly right there, there. Try to get this as symmetrically drawn as possible. There we go. So I'm chopping this up into standard deviations, meaning that this distance right here is 1 standard deviation, which we called sigma before. So that means that right here, this value sitting at this point occurs at mu plus 1 standard deviation, so mu plus sigma. And this point over here is at mu plus 2 standard deviation, so this will be at mu plus 2 sigmas. And then by the time I get all the way over to this one, we'll be at mu plus 3 standard deviations, mu plus 3 sigmas. And if I move the other direction from the center, I need to now subtract off 1 standard deviation to get to this point. So I go from the center and I subtract 1 sigma from that. So here's mu minus sigma. And over here, it's going to be mu minus 2 sigmas to get to this point. And by the time I get all the way over here, we're at mu minus 3 sigmas to get to all of these points. So these are kind of just the important points that I've chopped up this curve into a bunch of different values. You can also think of these in terms of z-scores. So right now, all of these as they're all written in terms of x. They have the units. Maybe these are ages, like we just saw with the driver's license example. Maybe it's weights, so in pounds or something like that. Maybe it's heights in inches or feet. It's some sort of measurement that corresponds, again, here to whatever x happens to represent, whatever the random variable x represents. But if we convert everything to z-scores, if instead we use z-scores, this is what will make this thing a standard normal distribution. So this has units of whatever the random variable represents. It could be a height, a weight, an age, etc. Could be a bunch of different things. Over here, I want to rewrite these all in terms of z-scores. Write this correctly here as a z-score. And I'll talk about this in an example in just a minute. But let's think about what the z-scores are. So remember, the formula for a z-score is the following. If I want the z-score, we take the value of interest, we subtract off mu, and we divide by sigma. I'm telling you right now that the value of interest are these points that we're interested in. These are the different x values. So for example, the x value right here is just whatever mu happens to be. It's the average value. What happens if I plug mu in for x here? Well, then I'd get mu minus mu. So anything minus itself is always going to be 0, and then I divide by sigma. So regardless of what sigma is, take 0 and divide it by some number. This is going to be 0. The average value, the z-score corresponding to the center of our curve, is always going to be 0. So we talked a lot about z-scores back in chapter 3. Here's where we really, really, really need them. And so if you weren't comfortable with them then, now's the time to make sure that you go back and review that and get comfortable with them. The z-score of a center of a curve, so the z-score that corresponds to the average value, is always 0. Remember, the z-score tells us how many standard deviations above or below average something is. Below average a given value is. So when I plug in x exactly equal to mu, if it's exactly at the average, then it's 0 standard deviations above or below average because it's sitting right there. It's at the average. But what about this value right here? Well, this is how many standard deviations above average? It was exactly 1 standard deviation above average. And we would see that if we plug this value in. So if I took this and I plugged it in place of x, what would we get? I would get mu plus sigma, there's my value of x. I'd subtract off mu, and then I'd divide by sigma. Well, I'd have a mu plus sigma and then minus another mu. The mu's would cancel, and I'd just have sigma over itself. So sigma over sigma. Anything divided by itself is always going to be 1. It's 1 standard deviation above average. So let me erase this real quickly. But this is where this is coming from, where I'm getting these values that I'm going to write down. It's from basically taking the value that we've written down here and plugging it into this formula. This has a z-score of 1. It's 1 standard deviation above average. What about this one? This is 2 standard deviations above average. This one is 3 standard deviations above average. Over here, it is 1 standard deviation below average, so it's negative. Over here, it's -2 because it's 2 standard deviations below average. And over here, it's -3. So these are the corresponding z-scores along our distribution. But we still haven't addressed the empirical rule all the way yet. The empirical rule tells me how much area I should associate with each of these regions that we got this thing chopped up into. And so here's where the empirical rule comes in. The empirical rule tells us that between these two particular values, so 1 standard deviation above average to 1 standard deviation below average over this region from z equals -1 to +1, 68% of the area shows up between those two values. And if I go from -2 up to 2, so if instead I go all the way out to here, so if I'm looking at the region from here all the way over to here, that contains 95% of the total area. And by the time we get out from -3 to 3, as you can kind of see by the picture, we've pretty much got everything that we need. Almost all of the area has been taken care of. And this is what is actually an option. It'll say almost all on the homework. The almost all is 99.7%, it turns out. So this is the empirical rule. These values right here, these percentages telling us what percentage of the total area falls into each of these regions are the empirical rule. So the empirical rule just specifies the 68, 95, almost all values. If your curve has 68% of the area between a z-score of -1 and 1, and 95 between -2 and 2, and almost all of it between -3 and 3, then you are dealing with a normal distribution. If we use the z-scores here, that's what makes it a standard normal distribution. So using z-scores, standardizes the curve. So what do I mean by that? Well, let me give you an example that can maybe put this into context a little bit better. Hold on, let me just grab this. Okay, so let's say we're talking about something related to, I don't know, lifespans of dogs. So let's say the lifespans of some certain species of dog let's say that they are normally distributed. And let's say that the average age of this species of dog, the average lifespan is 14 years. In fact, let's make it slightly different with a mean of, let's say, like 14, let's do decimals, 14.2 years. And a standard deviation of, let's say, 2.1 years. So again, standard deviation kind of tells us basically how spread out the lifespans are. If it's really tiny, then almost all the dogs would live really close to 14 years. The bigger this number gets, the more spread out the different lifespans are. Some live much older, some live much less. So that's kind of the idea here. So if you think about it, in this case, our random variable x is going to be the age of a dog. So basically the total lifespan. And it's measured in years. So if I wanted to ask a question like, what is the probability that a dog will live to, so what is the probability that a dog will live to be at least, let's say 16.3 years. What is that probability? Well, if we draw our picture of our normal distribution, this will make more sense, right? So it's given that the lifespans are normally distributed. They follow a normal distribution. That's the way that we would phrase this. Let me draw that as an actual straighter line. Here is my, oh, try that again. Here is my curve that's meant to be my normal distribution. This is x. Again, it's the age in years. And what is the center of this curve? The center is mu, but what did we just say mu is? The mu is the mean. It's 14.2. So if a dog winds up falling over here on this graph, that means it didn't live to be 14.2 years old. It's lived some age less than 14 years. And if it comes over here, it means that that dog lived to be more than 14.2 years. We said that a standard deviation in this case, which we ballpark is about that distance right there is supposed to be 2.1 years. This is the value of sigma, according to the problem that we just stated. And so what is, our goal is, in this case, to figure out what's the probability that a dog will live to be at least 16.3 years. Well, the question is, where does 16.3 fall on this graph? So where is 16.3? Where does it fall? Does it fall over here? Does it fall over here? Does it fall over here? Where does 16.3 fall? And then we can use the area associated with wherever it falls to figure out this probability. So where is it going to fall? Well, I know 16.3 is above average, so I know it must be somewhere to the right. And that rules out this option over here on the left. But it's not that much more than 14.2, so it's probably not this one way over here. We can figure it out by converting to the z-score. The idea is we're going to be finding these probabilities, these areas under these curves, using basically one of two tools. We're going to have either a graphing calculator / Excel, so some sort of technology, or we're going to use a table, and I will show you how to use this table going forward. To find areas under curves requires, again, as I mentioned before, it requires calculus, and we're not going to teach you calculus, so instead I'm just going to give you these technology tools and or this table to allow you to compute the areas without using calculus. But in order to use the table, for example, I don't want to have a separate table for this species of dog's ages. Right? I don't want to have a normal distribution table that has to do with this, whatever this species is, this type of dog, and the lifespan of this dog. And then I would need another table for the lifespan of a different species of dog. And maybe we're not interested in dogs. Maybe we're studying cats. I'd need a different table for the lifespan of this type of cat. Maybe we're not interested in lifespans. Maybe I'm interested in the weight of an animal. Well, we need a different table for that. Maybe I'm actually interested in the height of a tree instead. I'd need a different table for that. So even though we have all of these different things that follow these normal distributions, we don't want to have a separate table for every single one of them. But we don't need a separate table for every single one of them because we have, instead of dealing with all of these values, which again could represent a height or a weight or an age of a cat or a dog or a tree or a person, Instead of dealing with those values, if I just convert everything to z-scores, then it's standardized, and the center is always 0, and one standard deviation above it is always 1, and over here it's always 2, and over here it's always 3, and this is always -1 and -2 and -3, as opposed to the graph that we've got here where the middle is 14.2, and if you go 2.1 more than that to get this value right here, now we're at 16.3 when I add those numbers together, which incidentally is the number we were interested in. So right now, when the values are in terms of the age, we have a normal distribution. But if I convert everything to be in terms of z-scores, we will have a standard normal distribution, and it will be much easier to deal with. So that is going to be our step. I'm going to erase all of these. We know it's not that one. It's not this one over here. In fact, it turns out to be this value right here, because this is where 16.3 falls. If I were to take mu and add sigma, so take 14.2 and add 2.1 to it, when I add those two numbers, I'll get 16.3. So that's the value sitting right here. 16.3 is right there. Well, what is the z-score of 16.3? We can see that it's clearly one standard deviation above average. We should get a z-score of 1 out of this thing. So let's check and just verify. If I plug in the value of interest, 16.3, and I subtract off the mean, which is 14.2, and then I divide by the standard deviation, which is 2.1, maybe toss some parentheses around the numerator here. And if we do this on a calculator, let me bring up a calculator here. And let me clear our calculator, and I'll plug this in. So if I want that z-score, I can do my parentheses, 16.3 minus 14.2, close my parentheses, and then divide by 2.1. And hit enter, and what does it give me? It gives me a z-score exactly as I anticipated of 1. So the z-score here is 1. And that is going to be a much easier value to work with. So now that I'm done with this, let me close this back up and open these back up. And we can take a look at exactly what's going on here. Okay, so I found the z-score is 1. I'm interested in the probability that the dog will live to be at least 16.3 years old. So at least means greater than or equal to that. I'm interested in that the value of x, the age in years of my dog, is greater than or equal to 16.3. And we just saw that that's equivalent to looking at, because this z-score corresponds to z equals 1 right here, I'm interested in this region. These are all the values that indicate that our dog lived to be at least 16.3 years old, right? 16.3, anything to the right of that is older than 16.3, and that's what we were interested in. What was the probability that our dog lived to be at least 16.3 years old? So here's the region of interest. Here's the region of interest. We want that area. So the probability that x was greater than or equal to 16.3 is the same as converting it to z-scores, the probability that z was greater than or equal to 1. And if I want that area, I can use a little bit of trickery from what we've got up here in the way that we did this picture. I have some of these areas known, right? 68% as an area would be written as 0.68 if we convert this to a probability, which is an area. So area and probabilities are the same thing. Same thing here. If I convert this to an area, this is 0.95. 95% of the area is 0.95 because the total area is 1. And we're interested in this case, the equivalent of that area. That's what I'm looking for. So if I come back down to this picture, I'm going to just redraw it to make things a little bit easier to see. Get a slightly less cluttered version of the same picture. So you're probably going to want to do this as well. Get used to drawing this picture. So here's the z-score of z equals 1. This is the area that I'm interested in. What is that total area? Well, I don't know. I can't use the empirical rule to figure this area out, because all the areas that it gives me are these ones that are kind of centered around the middle here. So 68% between -1 and 1, 95 from here to here, and so on. But let me delete that last line I drew and draw it a little more symmetrically, hopefully. I know that this area is 0.68, right? That's between -1 and 1. And that leaves me with this combined area. If I were to shade both of these regions, the combined area must be everything that's left over. So what is left over? If the total area is 1, and this middle region that I've cut out is 0.68, the combined area is the leftovers, which is 1 minus 0.68, which equals 0.32. I know that the combined area of these two shaded regions is about 32%, according to this. But I also know that it's split evenly left and right. It's symmetric. The area over here matches the same area over here. So if I just want this area, if I just want the area on the right, this is half of the leftovers that we had, right? The leftovers was both of the shaded regions. This is just half of it. So it's 1/2 of 0.32. So if I take 0.32 and I divide it in half, I will get 0.16. And that is my estimation for this area. The probability that a dog is going to live to be more than 16.3 years is 0.16. And I found that by using some sort of clever tricks and some drawings here. I want you to get good at these spatial relations, but I will also film another video where I show you how to do all of these problems on a calculator or in Excel. And you don't necessarily need to have the visuals in mind, but it's really, really helpful if you draw these pictures. I would strongly recommend drawing pictures like this for every one of these problems that involves a normal distribution. So that's going to be it for the idea of a normal distribution. And again, a standard normal distribution is just one where instead of looking at the random variable units, which happen to be either height or weight or age, depending on the context, we're just going to convert every one of those values to z-score, and that is the standard normal distribution. And in the next video, we will just do a bunch of examples. I'll show you how to do a bunch of problems using both a calculator and Excel.